Hello and welcome back to part 2 of lesson 1 limits. So as I mentioned before, we are organizing the limits into groups so that we can classify the set of strategies that we need to use to evaluate each type of limit. So the first and one of my most favorite types of limits is the simple limits. To evaluate the simple limits, we simply substitute. See, it has the word simply in it. So we simply sub in the value of x. Okay? So in this case, we have the limit as x approaches 1 of x minus 2 over x plus 3. So that means that x is allowed to be 1. I will substitute and see if I can evaluate it by direct substitution. So that's negative 1 over 4, so that's the answer. So remember that in simple limits, we are able to evaluate the function at a point without having to do any work on the equation of the function. When this happens, it means that the function is continuous at x equals 1 because the limit is found in the same way as evaluating the function at a point. In the next equation, or in the next example, we have the limit as x approaches 0 of 2 to the power of x. So x equals 0 means 2 to the power of 0. The answer is 1. It's a real number. It exists. So the limit equals 1. The next question, the limit as x approaches pi of sine 1. This is kind of a unique question. So as you can see in here, in the equation of the function, we have a constant number. Sine of 1 is sine of 1 radian. If you use a calculator set to radian mode, you're going to find sine of 1 equal to approximately root 3 over 2. So if x approaches pi, it won't affect the value of sine of 1. So we're going to say that the limit as x approaches pi of sine of 1 equals sine of 1. And here I'm going to mention one very important rule about limits. So the limit as x approaches a of some constant number would always equal that constant number. Okay? Next question, the limit as x approaches pi over 8 for 3 cos 4x means 3 cos 4 times pi over 8 divided by sine of 4 times pi over 8 would equal 3 cos pi over 2 over sine pi over 2. Now cosine of 90 is 0, or cosine of pi over 2 is 0. Sine of pi over 2 is 1. The answer is 0 over 1, or simply 0. The next example, it looks complicated, but always check and see if you can just simply substitute x. So what we have in here is the limit as x approaches 0. So that would be square root 2 times 0 plus 9 minus square root of 5 times 0 plus 1 over 0 minus 4. So this would be root of 9 minus root of 1 over negative 4, or 3 minus 1 over 4 negatives, and that would be 2 over negative 4, or negative a quarter. Next question, the limit as x approaches 3 of number 45. Again, we're going back to the same rule we just explained. So the limit as x approaches a of some constant number would be equal to that constant number. So in our case, 45. So simple limits are pretty straightforward. But one thing that I want to emphasize, or one thing we want to take from them, is whenever you're asked to evaluate a limit, and trust me, you'll go over some pretty complicated ones, you should always first check and see if they are simple limits. So if they can be evaluated by direct substitution. For two main reasons. Number one, if it is a simple limit, your job will be done in few short steps. And if it is not, then you will understand why it's not a simple limit. You will understand, as a result, what strategies to use, because you will see what didn't work, right? So what made it impossible to evaluate by simple substitution can bring you closer to the idea of how to evaluate that limit, okay? So the next group of limits is what we call the indeterminate-form limits. Now, indeterminate-form limits are limits that you cannot evaluate by direct substitution. If you directly substitute the value of x in your first step, you will find out that the expression is undefined. Those type of limits come in various forms, okay? And they happen when functions are discontinuous at the point we want to estimate its limit. So some of the techniques that we use is, number one, the factoring technique. When do we use the factoring technique? Mainly when we see rational expressions. Okay, or rational functions. So we're going to start with the first one. They're kind of fun limits, actually, to evaluate. You will see. So, first example, the limit as x approaches 3 of x squared minus 9. Obviously, if I substitute by 3 here, I get 3 squared minus 9, 3 minus 3. I'll make a very quick estimation here that 0 over 0, that's undefined, okay? So what I'm thinking is, okay, so this is rational. I can try factoring. So x squared minus 9 factors to x minus 3, x plus 3. And then divided by x minus 3. As you can see, we can simplify the common factor of x minus 3. So the simplified form would be the limit as x approaches 3 of x plus 3. Now we can substitute x by 3, and we'll say that the value of the limit is 6. Next example is your turn to try, but I'm going to do it in here with you. But if you wish, you can stop the video and try to do this on your own. It's more fun that way. So the limit as x approaches 2, again, never forget, try to estimate the value of the limit by direct substitution always. So that would be 8 minus 2 to the power 3. So 8 minus 8, 0. So that's okay. Numerator can be 0. But then notice how denominator will turn into 2 squared minus 4, which is 0. So we need to factor. So 8 minus x cubed. Remember, this is the difference of cubes. I'm going to write out the formula in here just in case. So a cubed minus b cubed is a minus b. And then the other factor will have 3 terms. It looks like a perfect square trinomial, but it is not. So first and last terms are perfect squares. And the middle term is not double AB, but is a single AB, okay? So we're going to say that here we have 2 minus x. And then in brackets we have 2 squared, which is 4, plus 2 times x, and then plus x squared. And down in the denominator we have the factored form x minus 2, x plus 2. Okay, so we check for common factors to simplify, and what gets my attention is 2 minus x and x minus 2. They're pretty much the same, but notice that even though they have the exact same terms and a minus in between, you see that number 2 here is negative 2 here, and here we have negative x, a positive x. So the signs of each term are opposite. That means that these two binomials are opposites of each other. So I'm going to show the steps in here, but it's something that you can do it in one step. So So I'll show you what step we can cut out. So 2 minus x can also be written as negative x minus 2. So I'll check and see. Negative x plus 2, right? Or 2 minus x. And then 4 plus 2x plus x squared. And down here we have x minus 2 and x plus 2. And now we can see the common factor more easily. I will write the simplified form first. Okay, and we have 4 plus 2x plus x squared over x plus 2. And now I'll substitute because I see that denominator is causing no trouble anymore, because 2 plus 2 is not going to be 0. So we're going to say that we have a4 in here. 2 times 2 plus 2 squared divided by 2 plus 2. So once you substitute the numbers in, you don't have to write limit as x approaches 2, okay? Because here you're evaluating it. So that's when you lose this part of the expression here, all right? But it's important that you write limit as x approaches 2 in all the previous steps. So 4 plus 4 plus 4, that's a12 over 4. So it seems that the value of this limit is 3. Okay, let's do this together, the next question. So we have the limit as x approaches negative 1, x to the 5 plus 1 over x plus 1. Again, if you wish, you can pause the video and try the question on your own first. Remember, x to the 5 plus 1 is a polynomial of 5th degree, and then divided by a polynomial of 1st degree. You can tell that these are divisible by each other because the 0 of x plus 1 is a 0 of the x to the 5 plus 1 as well. So I'm going to go over the division process in here. Here I go. I'm going to do synthetic division. Now, it's something that we teach in the functions course, and it's a shorter way of dividing two polynomials. It has its disadvantages because you can only use this method when the divisor is in linear form. So if this is not something you're interested in, just skip ahead and continue with a regular long division. If you have x to the power of 5, that means that we have x to the 5 plus 0x to the 4 plus 0x to the 3 plus 0x to the 2 plus 0x and then plus 1. So what we are interested in is the coefficients here, which we list in the first row. So we have here, see, I'm going to erase this. So we have 1, 0, 0, 0, 0, 1. And the divisor is x plus 1, so negative 1 will go right here. So you get this negative 1, so x plus 1 equals 0, and x equals negative 1. Bring 1 down, multiply 1 by negative 1, then multiply negative 1 plus times negative 1 plus 1. Now multiply 1 times negative 1, negative 1, positive 1 here. And then we have negative 1 and then 0. So now we're going to stick the terms. So this is going to be a 4th degree polynomial, x to the 4, x to the 3, x to the 2, x to the 1, and then the constant. So we're going to say that this would be the limit as x approaches negative 1, x plus 1 times x to the 4 minus x to the 3 plus x squared minus x plus 1. And all this will be over x plus 1. So notice how x plus 1 now simplifies so nicely. And we get the limit as x approaches negative 1 of x to the 4 minus x3 plus x squared minus x plus 1. Keep that in brackets to show that the whole expression is inside that limit. And now we can substitute x by -1. So -1 to the power 4 minus -1 power 3 plus -1 squared minus -1 plus 1. So that's a 1. And it seems that the answer is 5. So we just looked at evaluating a limit by using factoring. Now we're going to move on to another method of limit evaluation, which is called conjugation. When do we use it? We use this when the expression is in rational form and it involves radical numbers. So use it in functions that involve, or I should say rational functions that involve radical numbers. So this is probably the more exciting part of this lesson. Okay, radical numbers or radical terms, okay? So what we have in here is limit as x approaches 9 of x plus 7 minus, in square root, right, minus 4 over x minus 9. If I substituted x by 9, then I would get the root of 9 plus 7 minus 4 over 9 minus 9. So 16 square rooted is 4 minus 4, 0 over 0. So it doesn't exist. So direct substitution doesn't work, which makes us think, what method can we use? Well, I see a fraction and I see radicals. In this case, we have to use what we call the conjugation method. Okay? So how does this work? I noticed that in this limit, or in this equation, I should say, the radical number is in the numerator. And what I want to do is conjugate the numerator so that I can somehow gain access to x in the numerator, so, and hopefully simplify it with a denominator. So here we go. I'm going to say that to conjugate it, I'm going to continue in here. I will multiply both numerator and denominator by the conjugate of the numerator, because numerator is the one that we are conjugating here. Numerator is the one that has a radical. And the conjugate of root x plus 7 minus 4 would be the root of x plus 7 plus 4. So here I go again, the root of x plus 7 plus 4. So that will produce the limit as x approaches 9 of long line here. Remember that here we have the difference of squares. That's how conjugates are related to each other. And that will produce root of x plus 7 to the power of 2 minus 4 to the power of 2. Down in the denominator, we don't want to do anything as of yet, and you must keep the terms in factored form, because factored form allows us to simplify, and that is our final goal here. So I'm writing all the steps. You can obviously simplify right away in here. But obviously I'm trying to show the work in here so we understand it better. So the square root of anything squared would be the anything. So x plus 7. And then we have minus 4 squared, or minus 16. And again, you will find this process a little bit tedious, but it is what it is. You got to keep on writing the full steps. Do not write part of the expression someday. So x plus 7 plus 4. So notice how the numerator now simplifies to become x minus 9. And the denominator has x minus 9. And that was expected to happen because this x minus 9 in here made the numerator 0. And this x minus 9 in here made numerator 0. So in other words, we are trying to simplify the zeros of this expression. So, and finally, the zeros surfaced in a more attainable form in here. So now we have the root of x plus 7 plus 4 here. Time to celebrate our hard work here. And we get the limit as x approaches 9 of 1 over root of x plus 7 plus 4. Now this is the exciting part. Try to substitute now x by 9 and see what happens. So 1 over the root of 9 plus 7 plus 4. So that would be 1 over root 16 plus 4, or 1 over 4 plus 4. Yeah, I know I'm writing all these very tedious steps. You can skip ahead, and you can go from here to the final answer, obviously. So 1 over 8, that's the value of the limit. Okay, now in the next example, I ask you to try on your own. The more you do, the better. I'm going to work on it quietly. Trying to work fast here. So x squared plus 7 minus x plus 13 over x minus 3. Direct substitution obviously doesn't work, right? So 3 minus 3 would equal 0. So we're multiplying by the conjugate of the numerator. Conjugate of the numerator is exact same thing we have, but not with a minus, but with a plus in between. Don't be afraid of having two radical terms, right? They will simplify. So, okay. And keep everything in brackets because you have binomials everywhere. So, again, difference of squares. X squared plus 7 minus x plus 13. Now, very careful that here you have a minus and you got a binomial from x plus 13 squared, right? This is going to need brackets, so I'm going to make this with thick brackets as a reminder for us. And then over x minus 3. So let's check and see what we get here. X squared minus x plus 7 minus 13. Plus 7 minus 13 is minus 6 over x minus 3. So still couldn't get rid of the denominator. That's our ultimate goal because there is a 0 hiding here that makes the expression undefinable. But I also see that I have a rational expression and I can possibly factor the numerator. So we are using conjugation and factoring here. So that would be x minus 3x plus 2 and divided by x minus 3. And chop chop, we have the limit as x approaches 3 of x plus 2, or 3 plus 2. The answer is 5. And also write an equal sign in every line to indicate that they're connected in order. I hope you're as excited as I am now. Moving on to a few more examples. This time we're conjugating the denominator. Example 3. Since the radical is in the denominator, we need to conjugate the denominator. Notice how if you substitute x by 1, we're going to get 1 plus 144 here, square rooted 12 minus 12, 0. Not possible. So we're going to multiply both numerator and denominator by the conjugate of denominator this time. So the conjugate of the denominator is root of x plus 143. You see how you have a minus in there, so that's a plus 12. And root of x plus 143 plus 12 here again. Equals limit as x approaches 1, long down line. So root of x plus 143 squared minus 12 squared. Numerator has x minus 1 and root of x plus 143 plus 12 in brackets. So again, so x minus 1, a root of x plus 143 plus 12. Please do not expand in here. You will just complicate your life. And down in the denominator, now we have x plus 143 minus 12 squared, which is 144. So you can see how things are happening in here. So x minus 1, you will find writing this numerator over and over again a little bit tedious. Again, be patient, because when you're patient, you can do a lot more. Okay, and you can think more clearly even. So, and it helps when you know what to expect, right? So x minus 1 simplified by x minus 1 now will leave us with, let me take this limit here, the limit as x approaches 1 of square root of x plus 143 plus 12. And now I can substitute x by 1 with confidence. 1 plus 143 plus 12. That would be root of 144, or 12 plus 12, and that equals 24. Here we go. So in the next example, we have the conjugation of the numerator. You can try this out. I'm going to skip ahead, and I'm going to move on to the last example for today. So in this example, as you can see, we have a rational expression, and this rational expression involves radicals in both numerator and denominator. If we want to simplify anything, we need to get rid of the radicals. And having radicals in both sides of the fraction suggests that we conjugate both numerator and denominator. So I'm going to highlight the numerator in pink. And I'll highlight the denominator in blue. So I will multiply first by the conjugate of the numerator. The conjugate of the numerator is root of x plus 3 plus 2 root x. Just like I multiply the numerator, I got to multiply the denominator by it. So root of x plus 3 plus 2 root x. Because I also need to conjugate the denominator, I will multiply both numerator and denominator by the conjugate of denominator. So another line here. So the conjugate of the denominator, here it is, the denominator itself, is root of x plus 8 plus root of 2x plus 7. So again, both root of x plus 8 plus root of 2x plus 7. I haven't actually changed the value of this expression because I've practically multiplied by 1 times 1 in here. So now we're going to marry together the pink stuff first. So these two will multiply to give difference of squares. So here we go. Sorry. We're going to say that this would equal the limit as x approaches 1. Long line here now. I want to bring everything in one rational expression. So we have root of x plus 3 squared will give x plus 3. And then minus 2 root of x squared. So that's the product, okay? And now we still have the root of x plus 8 plus the root of 2x plus 7. Now down in the denominator, we're multiplying the conjugates first, so the blue stuff. So that would be root of x plus 8 squared minus root of 2x plus 7 squared. And then multiplied by the other conjugate. So root of x plus 3 plus 2 root x. Okay, if you're having trouble understanding what we just did, just pause and go back. Okay, so it is important that we understand every single step before we move on. Knowledge based on confusion and heavy feelings can be a little bit difficult and it takes longer to process. So enjoy the freedom of stopping and going back. It's okay to learn or to hear something more than once, and we don't have to learn things right away. Always remember that. So we have the limit as x approaches 1. So now it's time for me to write this in a nicer form. So we have x plus 3 squared, which is x plus 3, the square root of it, right? And then minus, remember that number 2 here will become the power of both these terms, so that's 4 times x. And then we still have root of x plus 8 plus root of 2x plus 7. And in the denominator, we have root of x plus 8 squared, x plus 8, minus 2x plus 7. Okay, so let me highlight them now. So this is where we get this from, okay? And this is where we get this from. And we'll continue with the other factor, which is root of x plus 3 plus 2 root of x. So let's check and see what we have created in here. Hopefully something good, something that makes sense. So x plus 3 minus 4x equals negative 3x plus 3. And then multiplied by root of x plus 8 plus root of 2x plus 7. I'm repeating myself, but again, you got to write the whole expression. So patience. And down here we have x minus 8 minus 2x plus 7. So x minus x is negative x. And 8 minus 7 is positive 1. And again, root of x plus 3 plus 2 root x. All right, so we're going to take things a little bit further down here. Let me minimize the, let me zoom out here. Okay, so I think we don't need to go that far because we're almost at the end. Here we have more space. Now, notice how we have one factor in the numerator and one factor in the denominator radical free. So those are the potential factors that we can simplify. So if you check and see in here, the first has the x variable negative and the constant numbers are positive. It seems that we need to take out the greatest common factor. So one more before we simplify, one more step. So negative 3, and that will make it x minus 1. And then multiplied by root of x plus 8 plus root of 2x plus 7. Divided by, here we can take out negative 1 times x minus 1. And then root of x plus 3 plus 2 root x. So here is the exciting moment. And negative 3 over negative 1 is a positive 3. Root of x plus 8 plus root 2x plus 7. And then over root of x plus 3 plus 2 root x. And now we are going to substitute it and see what the value of the limit is. So 3 times 1 plus 8 square rooted plus root of 2 times 1 plus 7 over root of 1 plus 3 plus 2 root of 1. Again, here we get the root of 3. The root of 9, which is 3, right? And here we get another root of 9, which is 3. So we have 3 times 3 plus 3. And this would be over root of 1 plus 3, which is root of 4, or 2, plus 2. So the answer in our case would be 3 times 6, 18. Over 4, or 9 over 2. So we're going to say that this limit would equal 9 over 2. That's the answer. I'm going to stop the video now, and I will continue very soon with part 3 of lesson 1. See you soon.